the UAE regional group of the Institution of Structural Engineers. And welcome to tonight's CPD talk. We hold these talks once a month. We generally promote the discipline of structural engineering in the region. We also have a sponsor. You'll see the Hempel logo in the background. Hempel, who provide fire protection to steelwork, are our sponsor for the year. So check out the website if you get a chance. So tonight's talk is by Rudy Riachy from Ramboll. He's going to talk about computational design in the construction industry. So I will now pass you over to Rudy to start his webinar. Over to you, Rudy. Thank you.
Hello everyone. Thank you for the introduction. So I'm Rudy. I'm the head of computational design at Ramboll. And here today we're going to discuss how to think like a computational designer, what's the benefit and what's the uses for computational design. So we'll discuss first some examples, some big project examples, and then dive into other smaller tasks and dissect a bit more the importance of computational design as for engineers and architects in the AEC industry. So to start with, as an architect, so my background is architecture. And as an architect in an engineering consultancy office, it's a weird idea to think about it because maybe 2 years ago, I don't think there was Ramboll hired architects. But because I filled the role of a computation designer, and that is what they needed at that time, I was hired by Ramboll to support this role. And through computation design, I'm trying to help all the existing teams in the office, work with all my colleagues, with the engineers, and try to change a bit the workflow and the systems in the office. So a bit about my background. First, I worked for 5 years in an architecture and arts office with Nadim Karam Studio and the artist Nadim Karam. I worked for 5 years. We've done like amazing sculptures, large-scale sculptures and architectural projects. And during that phase, after graduation, I was on a self-learning process. And because I loved computation design, Grasshopper and Rhino, I pursued more this path. I started a bit self-learning throughout the years. And after 3 years of work, I decided to do a master's in computation design in Spain, Catalonia. And through the master's, it widened my understanding of computation design tools and how to think. I built up my skills. So after finishing the master's and working a bit more with NKS, I moved to Ramboll as to lead the computation design team. And since then, I've been almost less than a year almost at Ramboll, and we've done a lot of work and applied computation design in different projects. And to start with, the idea of what is computation design, for me, I split it into two. First comes the thought, so it's a way of thinking. Then comes the tool itself. So the most important one for me is you need to shift the way you think. You cannot stay like as you are. You need to evolve in your ways of approach on a project, approach on a problem, and you need to start using new tools, new thinking. And of course, everyone, like the older generation comes to me like he's 50 years old, 60 years old, he's a CEO, he's the owner of an office, he's a manager. But then to them, I say that computation design, they should know at least what is computation design, how to utilize it in their own work, how to help people train in their computation design. And for the young professionals and students, I advise them to start learning a bit more the tools, adding them as a skill set that would enhance their everyday work. And then comes the tool. So first, you know how to think, and then comes how to use the tool through this thinking and apply it. So let me explain a bit more maybe this was a bit vague, but through these examples, I'm going to show you that computational design was only the way to go with this project. Otherwise, it wouldn't have been done on the due time. So first, I'm going to talk about the gesture Beirut. The gesture is a sculpture, 25 meters high. It weighs 35 tons. It's made of steel beams, destroyed steel beams. After the explosion on August 4th in Beirut, some of you here might have heard of it. So there was this big explosion that destroyed the port, destroyed almost half of the city, and a lot of people lost their homes, lost their loved ones, and it was like a devastating times for the Lebanese people. And after a while, we had Nadim, the artist, had an idea to create the sculpture from the damaged steel beams on the port. So he did the sketch. On the left, you can see his sketch. It's a very simple line sketch. And on the right is the final result. And we had to do it in a crunch time of 6 months. 6 months of not only design, I'm talking design, fabrication, and construction on site. So everything in 6 months. So of course, here there's a lot of people who have some experience, and they know that 6 months is nothing compared to like a complex project. So we had to use computation. I had to use computation design to be able to match the deadline. So usually when we do these sort of big sculptures, we treat them as a building. So we have the design phase. So now we're thinking of the concept, how the destroyed hangar is being transformed into a sculpture. We did like some envision how we want it to be. And then I started working on the design. So the artist is, Nadim is around 60 years old. He usually does the sketches, and then we do, technically I do everything else. So I get his sketch, I try to create like these iterations and options from the sketch. And of course, I didn't model one by one everything you're seeing. I used coding using Grasshopper. Through scripting, I modeled, let's say, the skin, for example. For now, you're seeing like the skin of the sculpture. I was testing different orientations, different scaling. So to be able to do it very quickly, I coded it. So I also looked at the joints between the steel beams. We were testing different types of joints, different forms. And the cool part about computational design thinking is you need to always think about the data you have, the information you can get. Everything is important in computation design. So every design option I'm doing, it's backed up with data, and I extract these data and I compare them with the amount of steel. Let's say, for example, here I'm comparing the amount of steel I'm using through each option and how much steel is available from the site. So to be able to match, let's say, the scale of the whole sculpture and not use excessive steel while to try to utilize the most amount of steel that we have in the design. And you can start seeing during the design phase, as we started to think of how it should stand. This comes with experiences. I've done a lot of sculptures before, so using the steel materials. So having 3 points contact on the ground is very good as a structural advantage, let's say, in the design. And you can see like these two colors on the body. One is the main structure and the other is the bracing. So we're already thinking early on the structure with the design at the same time. And in a way, I'm doing it both. So I'm acting as an architect and as a structural engineer almost at the same time. Although I'm an architect, I'm getting some help from our engineering consultant, but the help I was getting is some guidance of, let's say, some spans of connections and stuff like that. So after looking at this, I was thinking about, okay, this is a nice design. This might work, but the only issue about this is how to construct it. We are a bit tight on time. I think if I give them this 3D model to construct, it would take the whole 6 months to construct it, because every point is flying in the air somehow, and you should locate it in 3D space. So I came up with this idea of, why don't we try to redesign it, but we start flat with a 2D layer. So the people on the construction site can start on the ground, build the first layer, and then the third layer would come like an extruded version of it. And we elevate it and we do the head, which is the only part in the 3D space, which is very easy compared to the previous design. And when I showed it to everyone, everyone supported this, the artists and even the engineers. And moving on from this step, the artist also wants to change, the architect or the artist also, as in any project, they want to create options, they want to create iterations. There were different designs of the sculpture and different emotions coming with the designs, the dynamic, the in distress, and the poetic. And each of these options, they have so many iterations. So if I want to spend each week to design one option with this iteration, the traditional way, we won't finish. So of course, going back to meshing and using some scripting, I was able to create all these iterations from these sketches. And eventually the artist chose the dynamic version. And this is what he liked. And this is what we took as reference. And going to site, I was a bit shocked by the scale of the beams. So when you work in the digital world, you're away from the actual site. When I came to site, no one can lift one beam. So you need to use these machines to lift every beam and to place them on site. But now the issue is we designed it with perfect beams, but actually the reality is these beams are destroyed. These beams are damaged beyond repair. And the purpose of our sculpture is to use these damaged beams to create this design. So what we had to do is someone came up with an idea of scanning, 3D scanning the beam. And it was for me the first time professionally working with someone on a 3D scan. What I expected is that the 3D scan company that we contacted, they were new in Lebanon. And they were like, I thought that what I expected from them is to give me each beam scanned in a nice 3D file. However, they gave me one big file, a 30 gigabyte file, hundreds of trillions of points. And what they did is they placed cameras throughout the whole site and they scanned everything at once, creating one big, huge 3D file. And what you see now on your screen is just like I cropped a version from this file. As you can see, they scanned the people, the machines, the floor, everything, the debris, everything is scanned. And you can see all of these are points. This is not a mesh. This is nothing. This is just points on top of points. So this was the first time working on this huge point cloud for me. So, but it wasn't that new since I already work on using computational tools. So I just learned a couple of software that will help me clean and then try to rebuild using meshing techniques and algorithms to remesh from these points and create these beams. But then these meshes are too accurate, and we thought that we don't need to exactly model all the minor damages. What we need actually is the full deformation. So what I did is isolated each couple of beams and then redraw them using some tracing technique in Rhino, and then using Grasshopper and Rhino, cleaning them and then redrawing them. And you can see how I extracted from the scan the beam itself in 3D. And this on and on until all the beams that were scanned are modeled. And you can see how cleanly they are modeled. And also you can see that these are labeled directly. And what I did is, after labeling them on my file, I went on site with a spray and started spraying the labeling onto the beams, not to lose each beam if someone moved it by mistake or something, to keep the labeling along. And then now my OCD is happy. All these beams are placed on one space. So now I know, so from here I got the data, how much linear meter of steel we have, the shapes we have, and the amount we have. So now we can go back to the design. We created this data sheet of the cross sections of these beams because they're different cross sections. These beams came from the hangars, some beams came from the roof, some were vertical elements. And so each beam had its own, let's say, size. We wanted to use the big sizes on the lower part of the sculpture. And now comes the real work, which is designing in a way. But now we're taking the 3D model that we did before and placing on top of it now the new beams, the real beams, the ones that are distorted. And I tried to benefit from these distortions. You can see like the hand is this one element beam that almost looked like a hand, it fit perfectly in that location. So it's like a design process where I tried to place the long beams to create the legs and the torso, and the smaller beams to create the hands and other smaller details. And after cutting some beams, also labeling them, tracing them. And we went from doing the primary structure, which is the white one, and then the black part is like a sort of bracing from the beams, and then we designed the whole thing from the actual beams themselves. Because we are like crunched on time, we don't have this luxury of designing and then sending to our engineering consultants the 3D model with the 3D geometry, and then them figuring out how to analyze the structure. What I did is I tried using Karamba, which is a plugin in Grasshopper. And although I'm not an engineer, but I understand through my experience, when I get these results, I understand what I can modify in the sculpture. So you can see, like, for the example, this small example, the one on the left and the one on the right, these are, this is a GIF, it's animated. You can see a bit the hand moving. So the sculpture on the left option, the hand is displaced more than the one on the right. And if you see, there's not much difference, but we added like these two red small pieces under the pit arm. So when I added these small two pieces while I'm designing, it affected 33% the displacement. And through these small decisions using Karamba and the actual beams, I built the sculpture. And then when I eventually sent the sculpture for the structural engineer to analyze, uh, he came back with maybe 15% of changes. Maybe he added some connections, some minor changes, but the overall look was more, let's say, well designed. It was logical for him. And this saved a lot of time doing the design and doing the analysis at the same time. Now back to, of course, there would be also post modifications. The artist might change some stuff still. And then these are some of the construction drawings. Because what we did earlier, I talked about how we were gonna build it the first layer on the floor. You can see how easy now on the left side, which is the first layer, they can just place them on the ground, weld them, and then place the green part on the right, on the elevated. And this was super easy on site. And you can see all this documentation on where to cut the beams and what beams we will be using and where. And also we had created these fabrication drawings with the location of each bracing. And even we designed this bird, which is on the top of the hand of the sculpture. And yeah, that's it. And then, although I was doing my master's in the meantime, I was working on this project and I was doing my master's. So I hope that someone else would take the charge in site work and monitoring the site work. But because the drawings are a bit complex and I was doing the whole process, eventually I went down again on site and I had them build the sculpture. And it was fairly easy. So we locate the key points on the floor, and then using the referring to my fabrication drawings, we were able to build it. I had to make sure that all the joints are clearly welded, and these are some pictures from the construction site. This is the site where the explosion happened, behind the sculpture. And you can see some zoom in shots on the head, how we were building it. And on the right side, I always try to double check our work. So since we had access to a drone, I would take a picture, go back to the office, overlay the drawing on top of the picture. And funny enough, you can see on the hand side, everything is matching except for the hand. The actual hand looks a bit lower than the red, the digital one. So when we went back to site, we fixed this. So all this double checking to make sure everything is on in place. Also, there was like the artist wanted like a sort of fountain coming outside from the hand, coming down like to a basin or like a pool, and then circulating the water, using the water for the fountain effect. And I made sure that the pipes, like this sort of stuff, weren't designed in the digital. These were directly on site. Sometimes when you're tight on time, you will need to work on site directly stuff. So we made sure that the pipes ran smoothly and were fairly hidden. And of course, there are other structural studies on the foundation. Also, there were some issues on how to elevate it and how to fix it and how to pour the concrete. And all of these studies were done, and we, through team effort, we found a solution on how to make it stand. And now the actual moving part, we used 2 cranes to lift it from the actual site onto a, let's say, a truck, and then the truck would drive it to the final location. And this is a picture I always look at it, and you can see that this sculpture came from the scrap on the right after the explosion. It's a bit emotional. It's a bit like giving a bit of hope. This is our, in a way, our way as engineers and architects to show that to the people our support. Maybe other people maybe lend some money. Our way is to design something for the city. Just to know that this sculpture was done without any support of as money. Everyone just provided his time and expertise to build this. And so here we lifted the sculpture and we placed it on site. You can see the scale of the sculpture. You can look at the picture on the right. You can see like small people trying to, I don't know why they're holding the sculpture. I don't know if they're holding anything actually, but you can see the scale of the people according to the sculpture size, and you can see it's almost like a building. And this should have been temporary, but it still stands there in Lebanon. If you go, you can see it on the explosion site in Beirut. And me as a, let's say, OCD, I wanted to make sure that the sculpture is really standing straight. So we did another round of 3D scan. I called the same company, and you can see the red line and how the sculpture is standing almost perfectly straight. And this is like the dream of every engineer, for his design to be as perfect as it can be. These are some drawings of the event and some drawings of the sculpture, and this is the end result. After finishing the sculpture, we had like a small discussion in the office of doing like a small mock-up model. We were thinking of first doing it by welding small pieces of metal, but then I told them, why don't we do it as a 3D printing? I had the 3D printer back then. So using Grasshopper and a bit of computation design, I was doing some different options. Since 3D printing is a bit, you can go wild a bit in the design. Did some iterations, some options, and eventually end up doing this design. And you can see the process of 3D printing it and the end result on the right side. And this is another, let's say, hobby, which is for me 3D printing. But computation design allows you also to go into these different, let's say, tools and use them. So this was for the first example. The second example I picked was from my master's. It was the Zollinger grid shell. So during my master's time, we teamed up for 1 month and we created this structure with the help of our teachers that reviewed our work along the way. And this structure was all done using only Rhino and Grasshopper 2 and using computation design tools. And it took 2 months of work between design. Also, you can see like these tight dues, and we're doing a lot of stuff within these dues. And you can see in this GIF, the process. This is like a script where it's we're creating the structure or the design. Also, we're trying to analyze the joints and how they move and the connections. Also here, we're trying to use Karamba to analyze the structure. The Zollinger is known for its like puzzle connection. So each frame would come perpendicular to the other one almost. And here we're trying different connections, doing mock-up models, testing the stresses and loads, and using all these data to get it back into the software and to make it the more we study it in the real life, the more realistic our digital world is, so that we can be as accurate as we can. And here they were testing the bracing and the connections. After that, we went into how we're gonna build it, the process, and we were thinking of we model every single detail in Rhino so that we don't miss anything. Also, the stand size structure that's covering it, we use Galapagos, which is an optimizing technique to find the best sheet layout, and then used also Grasshopper to automate the 2D drawings from these sheets. So technically, all the process was automated, So every time we did a change in the early on in the design, on the shape, everything else would update automatically. And that's the power of one of the power of computational design. But I don't want to only focus on computation design as the tool. Also, I want to focus on the thinking, as I mentioned before. We cannot get rid of the process, of the design process. You cannot, you need to still sketch, you need to still team up, you need to think of solutions. Computation design doesn't replace these steps. In fact, these steps enable computation design. As you can see, we try to measure the actual scales of stuff, the detailing of connections, and then using these information, this logic, to translate it through a code in a script and then design it. And then we would have more control over the design. And you can see everything we did was well designed and tested by hand first and sketched. And then we moved from this process to the actual code and eventually designing it. And combining this design process with scripting and model making and testing, you can see the on the right, the physical model is on top, the mock-up model, and the actual building is on beneath it, and you can see it's almost the same. If we Photoshop it a bit more, you won't know the difference. And that's the power of like having this design process well designed and all the data well plugged in our code and in our script. Then came the design building process. So we were in charge also of building it. So we made sure that we can lift every element, we can build it by hand without using any machinery. And after building it, the first thing I look at is details. As an architect, I love to see this part. So I took the pictures from the model and from the actual build structure, and I start comparing them side by side, which is a fun exercise to see how matching it is. And this is the outcome, and the end results were very satisfying. This structure was built for a school. It's a school for students with needs and like for special students. And this structure was used for outdoor activities, and they were used also for outdoor classrooms occasionally. And you can see how beautiful the structure is standing, very nice and well designed. So this is another way or another power of computation design through this example. Now, the last example, I was just thinking of how to try to show you that computation design is not only for engineers or architects, it's just a thinking and a way to translate a logic into anything. So I picked an example which is unorthodox a bit. And it ties a bit with a small story. So before joining Ramboll, I was gonna join a PhD program in Germany, and one of the interviews was one of the candidates that might be hired for this PhD program. They had this exercise for us, and the PhD program dealt with diatom shells. They were studying these cellular geometries, structures of diatom. A diatom is like one cell structure, and because it's one cell structure, the structure should be efficient, it should be good, and because nature is the best reference for us, so the part of the PhD purpose was to study these organisms and try to imitate their structural behavior or structural design, and then try it into real world design solutions. So the exercise would be me picking one of these diatoms, which I picked this one. Its name is hard to read. I read it once, Actinopithecus splendens. Okay, so I picked this because it intrigued me. I love the challenge. I wanted to show them that I can design it through computational design. And so I did some research about this. This was a one cell circular shape. It had like mountains and valleys. It had two layers, and each layer had a different sort of perforations. And this is like a small explanation of some observations from scientists and from what you see and from the picture. And this was the only microscopic picture that I have as reference. And now I show you the thought process of how I use computation design thinking and the logic of how to dissect a geometry and how to build it through coding. First, I took a circle, sliced it into like a pizza, into triangles, and then these triangles would form like these mountains and valleys. And then step 3 would be having them alternate and creating two different layers, because the structure is made from two layers. So I made sure there's two layers inside. And after creating the surfaces, you can see the red surface is different than this. These are the two layers, but the two layers are in a way intertwined. And you can see after this, I did some meshing. And then after the meshing process, I applied some algorithms to create these openings. And then these openings would vary as from the sides to the center and scale. And then this is the second layer with different, you can see the difference in the openings. The second layer has more circles in it, more perforations, and different scale of openings. And when you merge both layers, you can see on the left, when I merged both layers, it almost looked as the actual organism. And this is fine. This is like we modeled this. This was done through Grasshopper, but now comes the real results, where after doing this code, now you can play around with the code. So technically, when you design something through Grasshopper, you can go back and change stuff. So for example, now I'm changing the number of valleys and mountains, and you can see directly the geometry is updating now. I worked once, I built the code one time, and then all of these iterations, all of these options that you're gonna see are just like some parameters that I'm changing in my code. Here I'm changing the number of valleys and mountains. Here I'm changing the inclination angle. Here I'm changing the perforations, locations, and scale. So I have full control over the geometry. And also here I'm applying the same code, but on a different geometry. And I can assure you that I can use the same script to build a facade from the same logic, or a roof of a building from the same script, and it will apply to the roof. So this is, this script now had one purpose, to design this diatom, but then I can use the same script to design maybe a roof of another building. And you can see how computational design is not limited to one thing, and you can use it whatever you see fit. And you see, and I love the detail level. As you see, I always try to match everything at the detail level. I use some voxel algorithm technique to merge the two layers to have this organic feel, texture. And this is for the third example. And moving from the examples into this topic, which is very crucial, I think, for me and for everyone in the audience. This is talking about visualization. And as engineers, I know from my friends and my colleagues that they don't like to put effort on visualization, producing nice visuals, because they think it's a bit exhausting. It needs a lot of post-editing softwares like Photoshop, Illustrator, and usually they deal with the structure and the analysis, and they try to leave the other part for another colleague to try to do the nice visual from it. And I'm here to try to prove them wrong, and to push you to create your own visuals in a simple way. So here, everything you're gonna see was done only in Rhino and Grasshopper, and you will see the potential. So this is an example of an old diagram. It's a modular structure of a room. This diagram was used in a report. I was like, I don't like the style of it. I don't like the colors. I don't like the look of the diagram. So what I did, I proposed for them if I can redo the diagram in my way. As an architect, I would pick a color palette first, and then I would produce this diagram. So this is like the upgraded version from the old diagram, and you can clearly see the difference. But then when I showed them this diagram, they were like, of course, use Photoshop, of course, use Illustrator, or use all these post-editing techniques combined with Rhino or other software. And funny enough, I didn't use any of the above. I only used Grasshopper. So this whole diagram was built in Grasshopper. So I can have full control on the dimensions, on the cross sections, on thicknesses, on the type of structural system inside. I can close it, I can open. You can see how interactive the script can be. So even there wasn't any Rhino work. Everything was done through this script. Even you're gonna see after in the GIF that even coloring the diagram was done inside Grasshopper. And imagine I will do this one time, and for any upcoming project, any upcoming case scenario or exercise, where you can see here the colors and how you can put the color palette inside, and you can pick the colors. So I was saying that whatever in the future, whatever modular design I have or room I need to design, I open this script that I did one time, and then I can do multiple uses for it in multiple projects in the future. So this is another, like they say, strength using Grasshopper in visualization and in modeling. And you can see, since I did it in Grasshopper, and Grasshopper works very well as an animation outcome, I can create this animation for the client to explain the capabilities of the design, for example, or the variations that he can control from the script. So all of this between diagrams and animation, this all comes along with computational design also. Another case scenario is my sustainability team in the office. When they do the carbon footprint or carbon calculation of the structure, they usually do this graph, and they wanted to be consistent. So I created this script also, going back to scripting always, coding. I coded like this very simple visual bar graph that will update the color according to a certain number. So they can simply add any project they want, the results, and they punch in the numbers, and the visual itself, it will update the color, and the quality is always the same. It's consistent, and the visuals are nice. And you can see I gave them not one option, not two even. I gave them 4 options, different styles, different coloring, different layouting. So in this way, they can have more options to do quickly these diagrams. Also, even gave them a vertical layout. So if they want to place a vertical diagram in their project. So this ensures that when they use, this is like they used it, and directly after I finished the script, I gave them, and they used it directly on the next project. And you can see this is how they placed it in the report. And you can see it's always consistent. So if they're gonna do the next 10 reports, all of them will look the same, will be high quality, and will each diagram, instead of taking half an hour to do the colors and everything the traditional way, they would do it in 1 minute using my script. So this is like part visual, part efficiency. Another example is this competition that I was part of. In this competition, they wanted us to do the structural and MEP concept of the building. So the architects gave us the volumes, and everything you see here was done using only Rhino and Grasshopper. There's no Photoshop, there's no Illustrator. I removed the labeling because it's a bit still confidential, but you can see the style of the diagram is already done. Even these dashed lines or all these added lines are all done inside Rhino and Grasshopper. And all of this was maybe done in 1 day, half a day of work, and then any updates in the structure. And you can see this is like a zoom in on the structure. Of course, I didn't model them one by one. I used coding to model these trusses, to model these vertical elements. And then if they change in the height and the elevations, because this is a competition, and you know that architects in the competition phase, they change a lot in the design and the dimensions and everything, and they do big decision changes. And to be able to match the speed of the changes, doing everything in Grasshopper, the structures, the trusses, the detailing, would allow me to catch up with all these changes very fast and give them more than one option even. So this is like another case scenario on visualization, and at the same time using computation design to create these geometries. Another also example is this regenerative high-rise concept tower. You can see on the top of the tower that there's this crane sitting. And the concept of this tower is that this crane is permanent, and this tower would change its functions throughout time. So let's say in 2030, it has a certain program, but after 20 years, they want to change it from, let's say, residential to office building. But maybe after 20 years, they want to introduce new functions to the tower. So they want to keep changing the interior, but maintaining the mega structure. And to be able to explain this concept for the client, I needed to do like a straightforward, simple drawings. For example, this section paired with the diagrams on the left. So you can see in the section, there's this red steel structure with the vertical steel elements. And these are the mega structure. And anything in between these smaller levels are prefabricated wooden structure, 2D and 3D elements, either rooms or pallets and walls prefabricated that you can choose and choose the layout, and over time you can remove, let's say, a room, and then using the crane on top, changing the layouts of these prefabricated levels. And to do like a quick simulation of different layouts, I used a script to model these options. You can see on the left, this wasn't done manually, this was done through a script. So I would do random layouts quickly, so you can see like different layouts on the same floor. So imagine this layout would change after 20 years. They can see the changes. And what's easier than showing an animation of the concept? So you would place the layout in between. You would place these elements, you place these rooms and functions, and then when you want to change, you can use the crane on top and remove these layouts and change them. And this animation is very simple, straightforward. It was done using only Grasshopper in Rhino. And since I have already everything done in Grasshopper, I just did the animation very quickly. We're almost at the end. This is what I call a miracle work section. So this was a stadium. Also, it's confidential, but I'll show you what was the issue and how we solved it using computational design. So you can see the amount of structure inside the model. And when they came up to me, they were like, we have a very tight view, and they didn't update any of the trusses, and the architect did like a big change in the design, and they had 1 day to update the whole structure. And they didn't touch the trusses yet, and it's full of trusses. The whole stadium is full of different trusses. And they wanted me to help them to update all these trusses inside Revit. And you can see on the left side, all these truss types. Each one has a color code, each one has a dimension, each one has made of different cross sections, and there are like 10 or 12 types of trusses inside the whole project. And thinking just about one floor level to just draw all these trusses and the right dimensions, the right cross section, is, if you're using the traditional approach, you would never finish in maybe 2-3 days. And they wanted all these trusses in 1 day. So, and to be able to do it, you can see like this, the stadium has several floors, and this is like a zoomed in. What I received from them is PDFs markups of color-coded lines, and these lines, each line would represent a type of truss that will be placed at this in this location in the PDF. And to be able, so this is my input in a way, and to be able to do it very efficiently and quickly, I open Rhino and not Revit. And what I did is I took these PDF markups and I placed the exact location of these trusses and the same colors, and I matched the colors with the type of truss in the layers and in my Grasshopper script, so that when I put one line in my Rhino file, the Grasshopper would create the whole truss in 3D. So all I had to do now is just put the actual lines in the right layers, and then the script will do the rest of the job. It will do the whole truss. It will then push from Rhino, using Rhino inside Revit. It will push all these trusses into Revit environment. And then when I've finished pushing these trusses, you can see this outcome. So I gave them the Revit file separate, and then they linked into the main model, and everything was working perfectly. There was no errors. There was no like clashes with anything. Anything were perfect. The sync between Grasshopper, Rhino, and Revit was seamless. And we were able to pull it in 1 day of work. And this, because we did this script, and because the stadium didn't end on that due, and there were more dues to come, we kept on using the script on, and we reduced a lot of time of work. So let me just tell you, if you come to my screen, if I'm working on my screen, most probably you'll see Grasshopper open, Rhino open, Revit open, maybe eTabs open, several software at the same time open, and all these softwares are working together, communicating. And this is like the most use of computation design in our industry, is how we can benefit from all these software together. So I'm using Grasshopper to do this geometry and then push them into Rhino. I'm using Grasshopper and Rhino to create the model and then push it into Revit. I no longer design in Revit. I just design in Rhino and Grasshopper using code. So if I change the design, it will directly update in Revit. Same goes for eTabs. So if I link Rhino and Grasshopper to eTabs, I also can generate eTabs model very efficiently for the engineers to analyze. And then also this script on the right is the same script that I can link also to one-click LCA, which is a software that calculates the carbon calculation and can do the life cycle analysis of a project. So all of this is coming at the same time in real time. All of them are connected. When I change in one software, it updates in the other softwares. So I can do all options. I can generate different systems, structured systems, and all of them can be analyzed at the same time and be backed up with a lot of rich data. So then when we want to really choose the best layout, the best system for the client, we can prove it with all these options and all these attempts that we tried and iterations, and we can tell them that we chose the most optimized design. To end up with a small quote that I like from Neil deGrasse Tyson, he's an astrophysicist. He says, as the area of our knowledge grows, so does the perimeter of our ignorance. The moment you stop making mistakes is the day you can be pretty sure you are no longer on the frontier. And if you think about computation design should lie on the edge of our knowledge. We're always trying to learn the new tools, the new workflows, the new approaches. It's fine if we do mistakes. It's fine if we take a bit more time to learn the new skill set, but eventually it will pay off. And a lot of people always come up to me and tell me, Rudy, why do I need computation design? I'm already been doing it in Revit, using the usual approach, using AutoCAD, Revit, and other software, and I can finish the project from A to Z without using computation design. Well, then I always answer him that if you stay in your comfort zone, if you think that this is the only workflow that you will be working on, your competitors, your other colleagues, everyone will be building the skill set and they will do the same job much faster, better quality, and better results. And this will show up with time. And hopefully this presentation would help you at least look into computation design as a thinking, as the future. And don't forget, AI is a subset of computation design, and you know what's happening nowadays with the AI. And in the near future, everyone at some point will be asking if anyone is hiring and the requirements, there will be computation design as part of the requirements. You can already see it nowadays. Everyone's talking about it, but in the near future, it will be like an obligatory thing. You can no longer use your traditional approach because they're not so much efficient. And thank you everyone.
Thank you very, very much, Rudy. That was really, really interesting and fascinating work that you've been doing. So really appreciate it. If anyone has any questions, please type it into the Q&A box. There's a few questions come in, Rudy. So first one from Priscilla. With all that you know now about computational design, would you change anything about the design approach taken with the first project, the gesture?
This is a nice question because every time like a year passes, you learn more plugins, more tool sets, and you become more experienced in what you did. Mainly what I would have changed is the way we scanned and modeled the actual beams. I think that it could be more efficient. The other thing I know for sure that the way we analyze the structure, because the structural engineers don't know computation design, so I had to give them a simplified version for robot to be analyzed in robot. But I think it should have been analyzed fully using computation design tools and implemented without using traditional approach, which would have better results and more optimization. It's a nice question. Thanks.
Okay, good.
You missed one question before it about the MEP.
Yes.
I think. Yeah.
Yeah. How is computational design done in? How is it applicable to MEP?
Yeah. So just to answer for this, for all disciplines, computation in my office, I'm using computation design for all disciplines: acoustics, electrical, mechanical, electrical, plumbing, whatever you think of discipline, you can use in a way or another. You can benefit from computation design, either from a small task or a big workflow. Mechanical is filled with a lot of manual work, with a lot of calculations, with a lot of Excel sheets, with a lot of systems, and all of this in the coming time, you will see that there will be a lot of plugins, a lot of developments in this area. You feel that MAP is not always the most important field that's been focused on computation design, maybe simply because the people who are interested in computation design have the background of structural engineering or architecture. But now I can see more MEP people. We already have a team in our office that are looking into computation design as the MEP team, and they're trying to develop this area. So there's a lot of stuff you can do there, a lot.
Okay, thank you. Another question from Priscilla. How do you see the future of computational design in terms of its role in promoting sustainability in the AEC industry?
Yeah, this is this question was answered in an article I wrote not long ago. So computation design will play a big role in sustainability. Now, with the evolve of AI, I think we'll reach a point where you can know all the systems, all the problems, and how efficient you can be before even starting sketching the design. From the site size, from the height of the building that you can build, you can predict directly from the start the impact of your design on the environment. And using computation tools from environmental analysis into sustainable analysis and wind analysis, solar analysis, all of these are starting to emerge from computation design. And pairing everything together in the future, you'll be able to predict much faster the impact of your design on every step.
Yes, thank you. Question from Becky. Are you utilizing AI to support your design process?
Technically, yes. So in computation design, there are some plugins and algorithms that are already available that uses optimization techniques, and most optimization techniques are part of AI. Either they are monitored or non-monitored algorithms. But I think, like all these people who are creating these AI are going to these interesting industries like Tesla car or doing something for Google or ChatGPT. So these geniuses are going to these interesting topics, but we are left behind. So what we need to do is try to attract these people, and we need to collaborate. So they cannot do it alone. We cannot maybe do it fast enough as them, and we need to collaborate. And then when we reach this level, you're going to see that AI will serve engineering much more than you think, because engineering is all about logic, it's all about formulas. And if you teach the AI the same way as you teach a student in the university, the AI is much faster, doesn't make mistakes, there's no human error. So eventually in the future, I predict that engineers themselves will start building AIs to accommodate their own skill set in a way, and their own
Okay,
tools.
yes. Ahmed has a question now. Where to start? How do you start learning computational design and structural engineering? Good question.
Structural engineering. So I think first you need to check basics of computational design. Everyone should check the logic, because computation design logic comes from coding. So you need to get used to the coding logic first, like the base of computation design. And as you can see, I'm an architect, but all my work is between arts, engineering, anything but architecture that I showed you today in the presentation. This is not because I focus only on engineering because I focus to understand really the base logic of how computation or Grasshopper works. Then you can apply it to engineering, you can apply it to design, you can apply it to your own hobbies even. You saw my 3D printing. So when you understand fully the logic behind how it works, then you can apply use any of these tools for any purpose, as long as you understand the process. So as structural engineer, I would suggest there's a lot of YouTube videos. There's a lot of people on social media that try to give out tips and tricks and try to do these training videos. So try to follow these people, there's a lot of material on YouTube, so you can start from there. And from there on, you would start to understand more, and then you will figure out where in the computation design world you will narrow down your experience or focus.
Yes, yeah. Okay, I think Jawad and Mohammed have it's basically the similar question about where to start. So you've answered that. Next question: does your computation design application consider the material strength, the strength of the material?
Yes, it can. So when you ask about computation design, don't forget that people are creating these tools and they're creating them for the purpose. If the tool is to analyze a structure, they will put in the code the material thickness or the type. And yes, in Caramba and in other software, you can consider the material type and thickness and everything.
Okay. Next question: do you think AI would be able to write the scripting in the future as input for these programs?
It already is. So if you ask ChatGPT to code, so don't forget, computation design has Grasshopper, and inside Grasshopper, you can access C#, you can access Python. So you can ask ChatGPT for a code that suits Grasshopper, that works inside the environment of Grasshopper, but you need a bit of knowledge of how to edit the code or fix it if it doesn't work directly. But already AI is doing that. It's providing a certain level of code. In the future, of course, it will do a lot more.
Okay. A question here from Louise. What's the most challenging part of learning computational design, and why do a lot of newer aspiring designers still gravitate towards the more traditional methods?
Yeah. So these are like two questions. Let me first start with the first one. The most challenging part is to understand the logic of how the code works, of like how the tools work. You'll face a lot of problems in data trees and how to connect these lists of objects to lists of rules and functions. So this is like the main bump you will face, and when you solve it, everything else is almost easy. So, and for the second part of the question, nowadays, like what you're asking are architects that are not using, let's say, Midjourney, or are not using these AI software and trying to stay in control in the design process. But I showed you a lot of examples where it isn't related really to the design, or it's just you can do it faster. So you're doing the same exact thing. So there are things that you do that either way, if you're doing traditional or using computation design, the same outcome. These things should be done at least. But then when it comes to, let's say, creating a render from just a text, this discussion is a different type of let's say discussion that isn't my focus for today. But computation design, for sure, everyone will benefit from. It won't change the traditional. It will enhance your traditional approach.
Okay. So Sandinu has asked for the gesture, how do you assess the structural integrity of the damaged steel structure reflected in the computational design? The properties may have varied since it was damaged or corroded.
Yeah, that's correct. So we considered them damaged to the max. We didn't even give it a bit of credit of strength. It can hold zero strength in a way. So the minimum of strength it can hold. So this was done from actually not from myself. It was done from the structural consultant. He suggested to treat them as not to pick one element is good, one element is bad. Just everything is bad, and on this basis to have a safe design. So we picked the worst case scenario and we designed it on the worst case scenario to avoid like having some problems.
Yeah. Okay. Fernando has asked, is there not a conflict between the creation and design created by architecture and the logical uniform program computational design?
Is there not a conflict between creation and design created by architecture and the logic uniform? Computation design is logic. So if you're implementing a logic, it is there. So it's like it won't be different from what you're creating. As you saw in my previous examples, when we did the grid shell, when we did the sculpture, the creation process was part of the computation design process. Everything was in one. Because there's a logic of how we're creating things, what we're doing is translating this logic using these tools, and that's it. They're one entity. There's not two separate things anymore. And this is the benefit of computation. You're merging. You're no longer only an architect. You're no longer only an engineer. Now you can assess your design. You can check if it's sustainable without contacting anyone else. You can use these tools to check all of these on your own at a certain level, of course, but then require more assistance when you come on the detail level.
Okay, thank you. Next one, thanks for the great examples. What methods could you suggest to ensure quality and accuracy of multiple structural options that are generated during the computational design process?
So the cool part with computational design thinking, everything is backed up with data. So if everything is backed up with data, when you finish the structure system or the design, you can create another tool to analyze the design, to check if it's according to the safety rules, if the system holding itself, is it optimized. So you create another code to check your initial code. It's like a self-testing, and throughout these results, you verify your design, which is what you asked.
Okay, thank you. Question from Juris. AI or machine learning is dependent on data feed into them. Do you consider that AI is the future and will replace engineering?
Technically, nothing would replace engineering as a term, but engineers themselves, I think in the future will be different. I don't think you longer go to the university and study for 4 years, 5 years, logic and systems and formulas. With the development of AI and the new ways, I think the future would be you go to the university and you might study 2 years about this engineering formulas, logic, and another 2 years how to use AI and these new techniques to train them to do these tasks for you. And now in the future, I think engineers will become trainers, builders of AI, and then controllers, and then they make sure that the results are what they want, and they leave all these tasks that you usually do manually, you leave them for the AI, and you'll be like an overhead person.
Right.
And it will affect a lot the number of people working on a project. So you no longer need 5 engineers. You might need 2 engineers paired with AI or these tools that will enable them to do all this work with only 2 people instead of 5, for example.
Right, yes. Yeah. Question here from Hussein, who you may know.
Yes.
Carbon content is important now to pave the way for net zero carbon. How do you see computational design can calculate the carbon mass for our buildings?
Yeah, good question. For me, there is no excuse not to do carbon calculation and assessment on every option you have. Now your tools will enable you to directly outcome from every single decision you do, from every element you add, from every structure system you choose. You can pair it directly with the information of how much carbon emissions projected on the materials you chose and how they're impacting the design and the carbon emission. So since we have this, we have the responsibility to always pair our design and structure with sustainability now, and we should do it. Everyone should start doing it.
Yeah. Yes. Yeah. Question from Shapur. We already have spent a lot of time understanding how the structures behave and how the design sections to resist the forces. Do you think the university courses should be changed to learn how to use these types of programs?
They should at a certain level. So I'm always the advocate of having a pencil and paper and know your stuff, know how the formulas, know how to do everything handwritten. But that's it. Like you need to know it, but then you don't need to do it manually anymore. But you need at least to have the level of knowing the formulas without using any software to become like a good engineer. But then when you know this stuff, when you reach this level of knowledge, you no longer study how you apply it through the traditional means or manually. You need to start learning the new approaches and the new techniques and the new technology that will enable your work more. So imagine if I ask you a question, so do you prefer doing everything manual? So designing a nice structural system, coming up with a very nice structural design, and then spending all the time just modeling it and making sure the lines are touching and the nodes are touching, and spend like 2, 3, 4 or days or 1 week on just modeling it and proving it, and then the architect would change something, and you spend another 1 week, or versus you designing the system but using computation design tools to do all the rest of the work, so you can focus more on solving issues, designing, creating the concept, and leaving this work that usually takes time for the computer to do.
Very good. Okay, there's a few more questions come in from YouTube.
Yeah.
How do you think we can implement computational design in any company?
First, as I told in the presentation, first you need to know how to think as a computation designer, because if you don't know what is computation design, how to think about it, you cannot see how you can solve your current situation in the company. But after knowing what it can solve and its benefits and the ways of work, you can start formulating a plan, maybe hiring a computation designer, or evolving the skill set of your employees to try to do it in a better way. So first, start with the thinking. That's the title of the
Yes.
of the topic today.
Okay, and thank you. Haider has another question. I think it's the most difficult question of the day. He says that this is amazing. What happened to the drawing board and the T-square?
Wait, what? What drawing board?
The drawing board and the T-square. He's just commenting on how advanced this presentation is.
Yeah. This is a comment. Yeah.
Okay. Sajid has a question. Which is the best coding language to learn for using computational design as a structural engineer?
Just a small comment for Haidar. I showed you in the Zollinger. We still sketched. We still did manual stuff. We bent some papers. We tested stuff with our hands, and then we took this knowledge directly into the code. That's the difference. We're still doing this, but we're doing it at a faster pace or a higher level. Yeah, that's a cool.
Yes, yeah, thank you.
Yeah.
Yeah, okay, yeah, Sajita, which is the best coding language to learn when using computational design as a structural engineer? And
mainly for this one is C#, .NET, and Python. Usually these three are the main things. It differs from person to person, or from really what he wants to get from the code. But eventually, also more coding languages are emerging, and I think we'll end up with a lot of languages, and all of these codes would work with each other in a way in the future. But you can start with C# and Python, I think. Maybe Python is the easier level, and C# is good, and maybe .NET, which is C#.
Okay.
Choose 3 tools, which will be the best tool. If you want to choose 3 tools, but what do you mean by tools? Is it like computation design tools? So for structural engineer, there are plugins inside Grasshopper. So Grasshopper, I'm not considering as a tool. It's the main tool that we're using. I think Rhino, Grasshopper. Inside Grasshopper, there's Caramba for structures. There's Kiwi for structures, and there's maybe Kangaroo is good also for form finding. So these 3 tools inside Grasshopper are good. Pair it with tools that will enable your Grasshopper and Rhino to link to Revit, to link to ETABS, to link to Robot. These software that will help you communicate between software and between tools are very important too.
Okay, thank you. There's still some questions coming in from Juris. If AI is the future, can you say that any type of engineering will cease to exist?
I doubt any type will cease to exist. Like, you will still need an electrical engineer. You will still need someone at least designing something. Even if the AI designed the whole thing, you need someone to edit. You need someone to say if it's what you want or what not. In the near future, I cannot see anything replacing any big role. All the roles will be still there. All the positions are still there, but changes will be within the actual position itself. The way you work, the workflow, the thinking are changing, but you will still need an engineer, a structural engineer, to do the work. At least in the coming 20 years, 10 years, let's say.
Yes, okay.
So no worries.
Okay, Derek has asked, how are reviewing authorities managing to review designs made using these techniques?
The cool part, they won't know if they're done using these techniques or not. The outcome is still the same. If you usually give them a CAD format or usually give them PDF format or I don't know, a Revit file, a BIM file. Technically, if I did the whole thing on Grasshopper Rhino and then moved it to Revit, you won't know if I've done it in Revit or in Rhino Grasshopper and then moved it. So the same goes for the authority. What really matters is the outcome, and we're reaching the same outcome at the end of the day. But who's reaching more efficient, who's more optimized, who can show you more quality and more, let's say, data-driven decisions, that matters for now.
Yes. Okay, that actually brings us to the end of the questions, and I think 22 questions, Rudy. So appreciate your input in your responses. So that'll
Thanks.
bring us to the end of our session tonight. And again, I have to thank Rudy for a very, very fascinating discussion, and thank you very much for raising the awareness of computational design. And we appreciate it. Just for everyone, we were live on YouTube, and a recording of this CPD talk will be available on our YouTube channel in the next day or so. So thank you very much, everyone. Thank you again, Rudy, and we'll bring the